Okay, Chapter 5, Section 4, the definite integral. Okay, so starting with Section 4.9, we introduced this idea of antiderivatives. Antiderivatives are the reverse of taking a derivative, right? Undoing a derivative. And then in the first couple of sections of this chapter, we've continued to develop that idea, and we introduced new notation for it called the indefinite integral. Okay, well, in this section, we're going to further develop that idea with the introduction of something called the definite integral. The definite integral is often referred to as the area problem. And at first, it seems like it's completely unrelated and it's a whole new thing. We shall see in the next section, in section 5.5, that the indefinite integral, which arrived from our study of derivatives and antiderivatives, is actually connected to this new idea of the definite integral and the area problem. Okay, so what is the area problem? Okay, approximating areas. Let's say that we are interested in figuring out this brown area over here in this picture. Okay, so the boundary of the regions are the vertical lines x equals to 1, that would be this one, and x equals to 5, that would be this one over here. Let me highlight them. That would be x equals to 1 over here, this one. And then this one over here, which is the line x equals to 5. The x-axis, so this region right down here, x-axis. And then the top of this is the function f of x, which in this particular case is defined as 0.25 x squared plus 1. So this portion. Okay, so this shape defined by all four of these walls is the area that we're trying to find. It's the area that we're trying to find. We often abbreviate this description by saying it's the area under the graph of f of x, which in this case equals to 0.25 x squared plus 1, from x equals to 1 to x equals to 5. But then this is what we have in mind. So how do we find that area? Well, note that standard geometric area formulas don't apply to this region because it's curvy, right? Because of this curviness to it. The only thing that we know has a curvature to it in our standard formulas is the area of a circle, and this is not quite the area of a circle. It has nothing to do with a circle. Otherwise, standard shapes like rectangles and prisms and don't help us with this. We could do a very ugly approximation, perhaps by, say, let's draw in a line. We could say that it equals to, insert a line. We could go from here and connect it up to there, and then pretend that this is the shape, right, with a straight line there. And then we can think about this as a rectangle down here. Let's insert another line. Go from here and go across this way. And then we'd have two standard geometric shapes, a rectangle and a triangle. We can get a pretty good approximation that way, but that's not what we want. We want an even better approximation. We want something a lot more refined. And then, in fact, we want the exact answer. So we're going to begin with an approximation, and then that would lead us to a process that can get us to the exact answer. So what we're going to do is we're going to do something called the method of approximating rectangles. We're going to estimate this area by inserting rectangles. So, for example, so we're going to come in and we're going to draw in these rectangles. So they're going to have maybe like that, and then we'll talk about how tall to make them. But let's say something like this is an example. And then maybe from here we introduce another one, maybe like that. And then from here maybe we'll introduce another one, maybe like that. And maybe finally from here we'll introduce another one, maybe like that. So we're going to insert these rectangles into our shape. And then we're going to find the area of those rectangles. So that if we find the area of this rectangle plus the area of that rectangle plus the area of that rectangle plus the area of that rectangle right in there, if I find the area of all four of these red rectangles and add them together, that gives me a pretty good approximation of the area in brown. Clearly not the exact answer, since there's all these gaps here that we're clearly not counting. So it'll give us a pretty good approximation, but not the exact area, not the exact area. Of course, we can always get an even better approximation by including more rectangles, as we'll see in a minute. And so we'll be able to get as close to the real answer as we want to, as much precision as we want to achieve. And then we'll develop a way of getting infinitely accurate precision, or in fact, getting the exact answer, the exact area. Okay, so the first technique we're going to use is approximating areas using left sums. So we're going to begin this process by using 4 rectangles. It's a nice convenient choice given the particular values here. Notice that this is 1, 2, 3, 4, and 5, so it makes it very nice and convenient to make the base of each one of these rectangles equal to 1 unit. Very important, it doesn't have to be 1 unit. In fact, it almost never is. It's just a nice convenient place to start. But eventually we're going to let these base values be decimals. In fact, we want them to be very, very small decimals. We want to make eventually so many rectangles that the widths of each base are going to get smaller and smaller and smaller. But a good place to start, given these particular values, and just introduce ourselves to this idea, is to begin with 4 rectangles. Okay, just an arbitrary choice. Let's just start with 4 rectangles. So the interval from 1 to 5 is going to be divided, right? So the area we're interested in involves looking at the area underneath the function f of x that's trapped between between positive 1 and 5. So we're just interested in this area right here. So we're going to take that space, the space between 5 and 1, which is 4 units long, and divide it by 4 because we chose to do 4 rectangles to begin with. So that gives you a 1. If, on the other hand, we decide to do 6 rectangles or 10 rectangles, then we would divide by the appropriate number here so we can figure out the width of each one. Right? So we have equally spaced out values. They're all going to be with delta x. So let's note that. So the width of this guy is this delta x notation, which in this case is 1. But they're all the same width. Delta x, and delta x. Right? All the triangles have a base width of delta x. Now, the height of each rectangle, how do we figure that out? So this left rule, this left area rule, means that we've chosen to use the leftmost point in the base of each rectangle. So for this first rectangle 1, the leftmost point is the number 1. So we would come up to this point right there and use that height to establish the height of that rectangle. And this height is established by evaluating our function f at 1. That's how we get that guy. And to be more precise, I guess, it's really that this height right there is f of 1 that comes from there. That height there is f of 1. And then for the second rectangle, given that we're using the left rule, we are going to use the number 2. This point right there will establish the height to this rectangle. So this height right here would be the height f of 2. From there to there, this is f of 2. Good? F of 2. And for this triangle there, we would use, for this rectangle, we would use 3, which means that this height right here is f of 3. And then finally, for this rectangle, we use that height right there, which means that this is f of 4. F of 4. Okay, so then we have a width and a height for each one of these rectangles. We can multiply them all and determine the area of each one of those rectangles, add them together, and that would be my first approximation for the area. The sum of the areas of these four left rectangles gives a left sum, right? So again, the left is referring to the fact that the height of the rectangle was determined by using the leftmost point in the base of each of the rectangles. So we adopt this notation of capital L subscript 4 to let us know that we're using the left end rule to determine the heights of each rectangle, and that we're approximating our area with four rectangles. That's what this capital L sub 4 refers to. So each rectangle area is height, the value of the function at the left endpoint, times the width, which in this case was 1, right? We very conveniently created this question in such a way that delta x was equal to 1. Remember that delta x was equal to the 5 minus the 1 divided by 4. 5 and 1 chosen because these are the areas. The area we're interested in is bounded by the line x equals to 1 and x equals to 5. And 4 because we chose to do 4 rectangles. And this equals to 1. Okay, so this would then represent the area of the first rectangle. 1 is the base, and f of 1 represents the height. This represents the second rectangle, the third, and then the fourth. Now, keeping in mind the function, to get the actual number, we just have to evaluate our function at each one of these points to get the actual number. So for example, for the first one, this is achieved by evaluating, well, let me zoom into here. This is going to be 0.251 squared plus 1 times 1 plus 0.25 times blank squared plus 1 times 1 plus 0.25 times blank squared plus 1 times 1, and finally 0.25 times blank squared plus 1 times 1. Okay, so for this first one, if we evaluate our function at 1 squared times 0.25 plus 1 times 1, well, that just gives me this. So the result of all of this just becomes 1.25. 1 squared is 1 times 0.25 is 0.25 plus 1 is 1.25. Okay, next we plug in the 2 into here. 2 times 2 squared is 4. 1/4 of 4 is 1, and 1 plus 1 is 2. So that means that the result of all of this is just this 2. And likewise for the others. So we plug in a 3 into here, and we plug in a 4 into here. And so we get all 4 of these numbers. We add them together, and we get an answer of 11.5. Okay, so let's go back to this picture. Okay, so what this calculation is telling us is that this first area right in here, this area, the first rectangle, that area is 1.25 units. And that this second area right in here, that this second rectangle, the area right in there, that area is 2 units. And that this third rectangle, that area right in there, that whole area right in there, is equal to 3.25 units. And finally, that this area, for this last one, this area right in here, this whole area, that whole area is 5 units. Okay, so I'm going to add up the 1.25, the 2, the 3.25, and the 5, and the sum of all four of those is 11.4. That is my first guess for the area, the total area in brown. Clearly not a great guess because, as we can see, there's a lot of gaps there. Let me highlight them. So clearly, this whole space right here is not being counted. It's outside of those rectangles, and it is inside the brown region. So is this area right over here. This area is also not being counted, and neither is this area, and neither is this area over here. So there's a lot of parts that are not being counted, so clearly it's not a great initial estimate, but it's where we're going to start off. So the actual area, as we can see, is going to be a little bit bigger, and that's because the function is increasing. When the function is increasing and you're using left-end estimates, it's always going to be the case that your rectangle is going to end up being a little lower than the actual area that you want to estimate. So you're going to always underestimate it a little bit, right? So f of x is increasing, and the left sum L sub 4 estimates the area. So 11.5 is equal to L sub 4, which is definitely less than the actual area. Okay, now we're going to go back and attempt the same estimate, find the area underneath the curvature f of x equals to 0.25 x squared plus 1 between x equals to 1 and x equals to 5, except this time we're going to use the right end rule. So we're still going to approximate that area using 4 rectangles. Remember, 4 rectangles is just a convenient choice right now, but eventually we want to use more and more rectangles. But the difference now being that the height of each rectangle is going to be determined by the rightmost point in the base of each rectangle. So, for instance, in the first rectangle, instead of using 1 as we did before to determine the height of the rectangle, we're going to go over here and use 2. So that point right there, which comes from evaluating our function at 2, will establish the height of that first rectangle. So this height right here, the f of 2. The next one using 3. So for our the second rectangle, this will be the width, and it'll be the same width as before, right? The delta y, delta x. Delta x is equal to 5 minus 1 divided by 4, which gives you 1. So each one of these bases, the base of each rectangle, is going to be 1. That's a delta x. That's a delta x width. That's a delta x width. And finally, that's a delta x width. Good. Okay, so then that means that the height of the second rectangle will be determined by evaluating our function at 3. So it makes it, the height is f of 3. For the third rectangle, its height will be determined by using 4. So this height from there to there would be f of 4. And finally, from there to there, we establish the height of the last rectangle. Okay, so a very similar definition as before. So similar to the left sum rectangles, we developed the right sum rectangles. So in this situation, we use the letter capital R to represent that we're using the right end rule, and the little subscript of 4 to indicate that we're doing 4 rectangles. Okay, so each rectangle is going to have a height, a value of the function at the right endpoint times the width, which in this case is equal to 1. So f of 2 times 1 represents the area of the first rectangle, and we evaluate 2 with our function to get an actual result. So this is going to be equal to 0.25. Now 0.25 is the same thing as x squared divided by 4, just for the the sake of space, 0.25 is 1/4. So it just makes it a little easier to squeeze it into here. So this is going to be equal to 2 squared divided by 4 plus 1 times 1. And that'll give me the area of the first rectangle. And then the next rectangle will be equal to 3 squared divided by 4 plus 1. This will give me the height of the rectangle times the base, which is equal to 1. So times 1 plus 4 squared divided by 4 plus 1 times 1 plus 5 squared divided by 4 plus 1 times 1. Okay, so 2 squared, that's 4, divided by 4 is 1, plus 1 is 2, times 1 is 2. So all of this whole thing here, simplifies to that, and that represents the area of that very first rectangle, which is this whole area right here. So this represents the value of 2 units. Good. Next, we have f of 3 times 1. We evaluate the 3 with our function, and then we get this result. So 3 squared divided by 4, that's 9 divided by 4. 9 divided by 4 is 2.25, plus 1 is 3.25, so we get this result. And so this is indicating that the area of this second rectangle, this whole area, is 3.25 units. Likewise, the third one, the third rectangle, is going to be 4 squared divided by 4. 4 squared is 16, divided by 4 is 4, plus 1 is 5. So that means that the area of this third rectangle is equal to 5 units. And finally, the last one is 5 squared divided by 4 plus 1 times 1. That's going to lead to the 7.25, and that is then, of course, the area of the fourth and final rectangle, this guy right here, which is 7.25 units. And so we get that right there. Okay, so if we add all 4 of them, we end up with 17.5. And so that becomes my best guess for the area underneath the curvature of the function f of x between x equals to 1 and x equals to 5. Clearly, this is an overestimation. If you notice, the height of each rectangle is taller than the function value, or I should say the height of each rectangle covers a region that is clearly above the function. So there's all these little pieces that are going to be an overestimation. So this portion right here, this little extra little bit there, oh, that didn't look very good. So that portion there, and this portion here, and this giant portion there. Clearly, all of these make up an overestimated estimation, right? And then the biggest one over here. So observe that f of x is an increasing function, and the right sums r sub 4 overestimates the actual area. So the real area that we're interested in is definitely a little less than, strictly less than r sub 4, which is 17.5. Okay, so recapping, we are trying to find the area underneath the curvature, f of x equals to 0.25x squared plus 1, that the area that's below that function, that is above the line, above the x-axis, between the points 1 and 5. We used the left sum rule to create rectangles whose heights were determined by the leftmost point in each base. And we got that that estimate was 11.5. Because we know the function is increasing on this interval and we're using the left endpoint, we know that our estimate is going to be below the actual answer. It's going to be an underestimate. Next, we used 4 rectangles to figure out the right sum rule, or the right sum value of 4 rectangles using the right sum rule. And we found that answer to be 17.5. Right? So again, the right side rule means that we use the rightmost point at the base of each rectangle to determine the height of the rectangle. And because the function is increasing and we're using the right end rule, we know that we are overestimating. The sum of all 4 rectangles are clearly, the sum of those 4 rectangle areas is clearly larger than the actual value we want. So we can establish this 3-part inequality. The real answer we're interested is trapped between these two values. It's less than R4, it's less than 17.5, but it's greater than 11.5. So we have an estimate for the actual area based on L4 and R4. Well, I mean, it's better than nothing, but that's still not a very great estimate. There's a whole lot of room there between 11.5 and 17.5. So to get a better estimate, what we want to do is increase the number of rectangles. As we increase the number of rectangles, the sum of the rectangles will give us a better and better and better approximation for the real area. Here's an app that will help us visualize that. So here's a nice applet available on the internet at this address right up here that will help us visualize this approximation of an area by rectangles. So I typed in the equation right up here, 0.25. In fact, let's just make sure that it's capturing it well by wrapping it around parentheses. So 0.25 times x to the second power plus 1. So there's our equation, right? So this one up here, the one in the blue, is the equation of it we're interested in. And we were interested in the area below that function, above the x-axis, but then sandwiched between the vertical lines x equals to 1 and x equals to 5. That's what these two values are in here, interval between 1 and 5. Okay, so we started off by saying let's approximate it with 4 rectangles. So 4 rectangles using the left end rule, and that's what they would look like. So here are 4 rectangles. We went through and actually calculated the specific values of these points and we got a specific answer for it. And then the computer here automatically calculates it for us. So the answer is 11.5. So 11.5 is the sum of these 4 rectangles. Now the computer here automatically tells me what the real answer is. So let me get rid of that. Don't worry about this, how it got this yet. That's what we're trying to establish in the next couple of sections. But for now, let's just accept that the real answer is 14.3335533. Okay, that's the area, the exact area of this gray region here that we're trying to approximate. So when we use 4 rectangles using the left endpoint rule, so for each rectangle, the height is established by using the point farthest left within its little base and then evaluating our function at that point. Right? So for this third rectangle, the point to the farthest left in its base is this point, and that's how we establish the height. Okay, so the sum of all 4 of these is 11.5. Next, we use the right end rule. So now the exact same area we estimate it by using the right end rule, and we get these rectangles. The right end rule means that each rectangle, the height of each rectangle is determined by the point which is the farthest to the right within the base of each rectangle. So for the first rectangle, the 2 determines the height, so f of 2. For the third rectangle, the 4 establishes the height. F of 4 establishes that height. Okay, and then the computer here automatically calculates it for us, 17.5, right? Hopefully that matches what we got. And again, we can see that the real answer, 14.33, is less than the 17.5, but more than the 11.5. The real answer is sandwiched somewhere in between the two. Okay, so that's what we got so far, but now let's go back to thinking about the left-hand rule. So if we want a better approximation, what we want to do is increase the number of rectangles. So from 4, let's go to 5. Oops, okay, 6. Let's go to 6 rectangles. 1, 2, 3, 4, 5, 6. You see that this is going to be a better approximation than back when we only used 4. Keep an eye on these gray gap things that we're not counting. They're going to get smaller and smaller as I include more and more rectangles. So instead of 6, let's jump up to 10 rectangles. That's an even better approximation. Now luckily this computer program automatically calculates the sum of all 10 of these rectangles, which is 13.13. I think it was 11.5 when we only had 4 rectangles, so the area has increased now. And we can see that it's getting closer and closer to the real answer. We have the benefit of being able to see the real answer right here. And as I do even more rectangles, 11, 12, 15, 20, right? As I do more and more rectangles, let's stop at 30. When I do 30 rectangles, we can see that the sum of all 30 of these rectangles is going to be a pretty good approximation. Already it's beginning to get a little hard to see the little gaps there. They're still there. If I zoom in, we still see that there are gaps, but they're getting smaller and smaller and smaller. So at least to the naked eye, it's starting to look like a pretty good approximation. And we can take this out even more. So at 40, oops, stop at 40. At 40, it looks even better. And from here, I can see that the sum of 40 rectangles is 14.035, very close to the real answer, 14.33. And as I keep going, let's go up to 50. Okay, even better. Let's get really crazy here. Let's go up, 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 up. Let's make it all the way up to 99. I think it only stops at 99. Oh, that was 100. Look, at 100 rectangles, the sum of 100 rectangles is going to be a very, very good approximation to our real answer. The computer again calculates the sum of 100 rectangles to be 14.2136, and that's really, really close to the real answer of 14.3355. Note that in every single case, the sum of the rectangles, no matter how many rectangles, was always a little lower than the real answer. So we've been creeping up to it from below, getting closer and closer, but always below it. That's because we're using the left-hand rule and because the function is increasing. Okay, now let's go back to the other direction. So let's go back to 4 rectangles, and let's go back to using the right-hand rule. There they are. And now, again, as we increase the number of rectangles, we see that the overestimation is going to get smaller and smaller and smaller, so that the sum of these yellow rectangles now slowly but surely becomes a very good approximation. Let's stop at 50. So again, the computer has this benefit of finding the area of 50 rectangles for us. And at the moment, we see that it's 14.5744 is the sum of 50 rectangles. And that's just a little bit more than the real answer of 14.333. Okay, so we'll keep going. Let's get it up there. And we see that it's just getting better and better and better and better and better. Stop at 100 again. Okay, so at 100, we see that the sum of 100 rectangles, each one having a height determined by the right endpoint rule, we see that that sum is 14.4536, very, very close to the real answer of 14.3355. And again, in this case, every single approximation using rectangles of size, we started at 4 and jumped up all the way to 100. In every single case, the sum of those rectangles was always a little bit bigger than the real answer. And that's, again, because we're using the right-hand rule and the function is increasing. So we are always going to overestimate. Now, in reality, we might not actually know this, right? We were trying to find the answer, so we won't know this. It'll be an unknown value. It'll be an unknown value to us, but we can approximate that value by choosing an appropriate number of rectangles. Now, obviously, we're not going to ask you to calculate by hand the sum of 100 rectangles. We might ask you to do it for something manageable, like we did here with 4 rectangles, or maybe 6 rectangles, something like that. You can expect to see something like that on your homework. Just know that this is an approximation, and that as we increase the number of rectangles, we'll get better and better and better approximations. Okay, so if we divide our subinterval from 1 to 5 in this particular case into more subintervals of equal width, and then computing the left and the right sums for this larger number of rectangles gives better approximations. Okay, so here is the results of using 8 rectangles. There's 1, 2, 3, 4, 5, 6, 7, 8 rectangles. And as pictured, they're all right-hand rules, so they're an overestimation. So this picture matches with this value right in here. Okay, so even though it's not displayed, here is the result of using 8 rectangles and the left-hand rule. And the point is that our real answer is somewhere between the two. The real area is trapped between this, in the middle of this 3-part inequality. It's somewhere between 12.875 and less than 15.875. If we up our game and use 16 rectangles, then we can see that the real area now is less than 15.09 but greater than 13.59 using 16 rectangles. And finally, if we really want to get serious about this and get a very, very nice approximation, we can use 200 rectangles. So the sum of 200 rectangles, each of them having a height determined by the leftmost endpoint in the base of each rectangle, the left-hand rule, we see that the sum of all 200 rectangles is 14.27, whereas using the right-hand rule and summing 200 rectangles gives you 14.39. So now it's a much better approximation. So the more rectangles we use, the better the approximation. We can reach any level of precision, and we can also, well, we can't get the exact error because in practicality, we won't know what the real area is, obviously. But we could get an idea, a sense of how much error there is in any particular approximation. Okay, so what exactly do I mean by error when I talk about error? So the error in an approximation is the absolute value of the difference between the approximation and the actual value. In general, neither the actual value nor the error in approximation is known. However, it is often possible to calculate an error bound. That is a number, a positive number such that the error is guaranteed to be less than or equal to that number. So back to this free online graphing tool, we have our equation here, 0.25 x to the second power, x squared, plus 1. Okay, so we're integrating between 1 and 5, and of course this online tool just tells me what it is and what the answer is. So we want to find this gray shaded region right in here. This is the exact area we want. And the computer calculates it for us. It's exactly 14.33. Okay, so that's the answer we want. And so what we're doing is we're approximating this with rectangles. So let's just, pick 5 for now. So if I had 5 rectangles, an approximation using the left-hand rule, so left-hand rule, they look like that. So if I calculate the sum of all of these rectangles, then that would be my guess. That would be my approximation for that gray zone. Obviously, not a perfect approximation. There's a lot of material missing, a lot of area missing. All this gray stuff right here, this it's almost a triangle, not quite a triangle because it's kind of curvy, but this almost triangle indicates for us, it shows for us all the area we're missing. The sum of the 5 red rectangles is definitely less than the real answer. Okay. On the other hand, if we use the right end rule, we create those. Now in this case, we are overestimating it. The gray region is down here, and then all these little tips, again, they almost look like triangles, but they're not because this thing is curvy, right? So these little areas here are extra. We're counting too much. We're overestimating the real answer. The error is the difference between the real answer, which is that gray zone, right? So here is the real answer. The real answer, which is 14.33, and the estimation, which is in this case the sum of all of these rectangles. Well, the computer automatically calculates it for us. At this point, it would be 16.84. This is the sum of all of these rectangles. Okay, but in practice at this point, we don't really know what the real answer is, so we won't really know what the difference between the two will be. That is the definition of error. If I take this, 16.84, and I subtract the 14.33, that'll give me the area of this space here that I'm overestimating, and then that would be the error. Okay. On the other hand, if I use the left-hand rule, I take the sum of all 5 red rectangles, that's 12.04. The computer automatically calculates it for me. And if I subtract off the 14.3355, then the difference between those two will be the error. Okay, so again, because we have the benefit of the computer program here, we know the real area, so we can actually write down the error. Okay, so now obviously it's a positive answer, but if I want to write down kind of a rule for it, error is equal to the real area minus the estimate. And since we don't really know whether the estimate is going to be positive or if the estimate is going to be bigger than the real area or smaller than the real area, this difference, this subtraction might result in a negative number. So we fix that, or we anticipate that, and we fix it by wrapping it around absolute values. That way we guarantee that whatever answer we get is a positive number. It wasn't really needed here, since obviously 14 minus 12 is going to be a positive number. But if we just follow this little formula, we'll always guarantee that the error is an actual positive number. All right, now let's take a look at the other one. Okay, so here now if we use the right end rule, we clearly overestimated. So if we follow that little rule, the error. Okay, so we follow this little rule that the error equals to the absolute value difference between the real area and the estimate. Then, so the error is equal to 2.5045. In terms of the picture, the error can be found by this. This extra little piece right there is the difference between the real answer and your estimate. So the sums of these almost triangles, like a triangle with a curvy side, the sum of all of these ones is the error. Okay, looking at the other one, in this case, the sum of the errors is the gap here, the gray almost triangle, this one, or this one. If we sum up all of these almost triangles, almost a triangle, they have 2 straight sides, and it is a right corner there, but the hypotenuse of it wouldn't be a straight line. It's got curviness to it, so it's not quite a triangle. But if I add up all of these red ones here, that should be this answer right there. That is the error, the difference between the real area and the estimate that you created by summing up a certain number of rectangles. In this particular instance, what we did is we found L, this is the left end rule, right? So this is L sub 5. And in this case, over here, this one was R. We used the right rule, right? R sub 5. Okay, and that's our estimate. Okay, well, like I said, in reality, when you're working with this in your exam and stuff, you're not going to have a computer to calculate the real area. So if you can't know this, if this is unknown, well, then you can't figure out this error that's unknown. So we won't really be able to figure out the exact error, but what we can do is do an upper bound for it. Be able to come up with a number such that the error is definitely smaller than that. And we do it in the following way. Okay, let's go back to our applet. Remember, this is the area we actually want. This is the real answer, that gray space there. When we use the left end rule, we ended up underestimating it. And then we can see all the gaps that we didn't actually count. If we found out those areas there, that would be the error in this estimation. On the other hand, if we use the right end rule, we overestimate. We can see these little extra spaces there are the overestimation. And that would be the error found in this estimation. Let's put them both together. Let's put them like that. Okay, so under one calculation, when we use the right end rule, the overestimation, the error, was found to be the sum of all these almost triangles here that I'm drawing in red. And under the other estimation, the error was found to be these almost triangles that I'm drawing here in green. So the sum of all the greens is the error from one estimation. The sum of all the reds is the sum of the other error. The sum of all the reds is the other error under the other estimation. And those are often impossible to actually figure out. Especially, well, if you don't know the real area, then you can't figure them out. But what we can do is say the sum of the red ones is less than the rectangles created by the two of them together. Okay, so in other words, if I think about, let's see if it looks okay highlighted about in blue. How does it look highlighted in blue? If we think about this rectangle right there, all of that, then the red is smaller than the entire highlighted. True. And the green is smaller than the entire highlighted. Good. Coming back over here, now let's look at this one. Look in yellow. In this little rectangle, then the red is smaller than the entire highlighted rectangle. And the green by itself is also smaller than the entire rectangle. So we can do that across for the other ones as well. Now, okay, so all the ones that I highlighted, if I add them together, they would definitely be equal to a number that is definitely bigger than the sum of the red ones by itself, and it's also going to be equal to a number that's greater than the sum of the green ones by themselves. And that is the estimate we're after. Luckily, the sum of all those highlighted rectangles is actually easy to figure out. Okay, if we extend a line from here all the way out to here, okay, so for the purpose of visualizing what I'm about to do, all I did is I extended lines that went straight across like this, and then created these little triangles here. So let's think about this thing I created here. What I want to say is that this rectangle right here is going to be the same as this one. Okay, it's got the same height, clearly. And we want to say that all of these have the same delta x for all of them, right? That's how we created these things. Delta x, delta x, delta x. So this is going to have the same delta x, delta x. Remember the formula for delta x is the same everywhere. Delta x is equal to b minus a divided by n. In this particular case, we were doing 5 minus 1 divided by 5. So it equals to 4/5. 4/5 is the delta width. Okay, and now this this rectangle here is the same as that one. And this rectangle here is the same as that one. And this rectangle here is the same as that one. And finally, this rectangle here is the same as that one. Okay, so finding out the sum of all these highlighted rectangles is going to be the same as finding out this. Where the width is delta x, that's fine. And then what about the height? Let's figure out the height. Well, the smallest possible value comes from here. If we trace it back, it comes from here, which if we trace it back to here, it was the value 1. Okay, so this is a height of f of 1, and that traces back to here. Right, so this has a height of f of 1. And then the tallest one comes from here, which is the output value from plugging in a 5, right? We're integrating from 1 to 5. So this is the value of f of 5. So this is the result of that guy. So if we want to find the height of this thing, then this height right there is f of 5 minus f of 1. Now in this particular drawing, just the way the characteristic of our graph, it turns out that this one is the tallest one, and this one to the left is the smallest one. But in a different equation, it might turn out the other way around. So it might turn out that this ends up being a negative number. So just to prevent that, because we want an area, so we want to make sure it's positive, all we have to do is wrap it around absolute values just to guarantee that that answer is positive. Okay, so what we're saying, again, just to confirm, is that if we think about the areas in red here, this is the error, the sum of the red. So let me zoom out here a little bit. So under one estimate, the sum of the red is equal to the error under one type of estimate. And that is definitely less than the sum of these highlighted areas, which is going to be equal to f of 5 minus f of 1 absolute value times delta x. Right, we can actually calculate it all. We know what delta x is. We know how to evaluate f of 5 and f of 1, so that's fine. On the other hand, if we just calculate these almost triangles that are right here, right, these almost triangles, that would have been the sum of all of those would have been the error under a different estimation. Sum of the green is equal to the error under a different estimation. So this one was by estimating L sub 5, and this one is by, R sub 5. So I'll put the error evaluated under R sub 5 when we're using the right-hand rule. We got all those, we overestimated and we got all those red areas. And then when we used L sub 5, then we got this error. And in both cases, as we can see from the picture, we're going to have the sum of the green ones is definitely less than the sum of all these highlighted rectangles here, which is going to have an area of f sub 5 minus f sub 1, absolute value times delta x. Okay, so I hope that's nice. Your author offers a nice little graphic for this. Maybe it might be a little bit better than mine. So let's see what his looks like. Okay, so here's the graphic found in your textbook. Pretty nice. So again, when we do one estimate, we find that the error under one type of estimate might be like these little red almost triangle things down here. And then when we do, and we keep going, And then when we do the error under a different estimate, we might be overestimating it, and then the error might be the sum of all of these green ones that are above the function f of x. So we might be overestimating it. Okay, so because we can't actually find the sum of all of these little green almost triangles, and we cannot find the sum of all of these almost red triangles, then what we can at least do is find the sum of all of these triangles, the sum of all of these rectangles, so that this rectangle is equivalent to this one, and this rectangle is equivalent to this one, and this rectangle is equivalent to this one, right? And so on and so forth all the way down. And so the sum of all of those rectangles, well, they're going to have the same width as all of the rectangles. They all have a delta x width, right? All of these rectangles, they're all delta x, all of them. So if you're just transferring it over, well, this is also going to have a delta x width, delta x. And now the height, well, the smallest one is going to start here at f of 1. And then the tallest one goes all the way up to there, which comes all the way over here as an f of 5. So say somewhere around there is f of 5. So that is the height. We got a giant rectangle made up of all these tiny little pieces. Its height is f of 5 minus f of 1, and its width is delta x. Okay, theorem 1. Error bounds for approximating an area by left or right sum. So if f of x is greater than 0, and is either increasing on a, b, or decreasing on a, b, then the absolute value of f of b minus f of a times b minus a over n is an error bound for the approximation of the area between the graph of f and the x-axis, from x equals to a to x equals to b, by either L sub n or the R sub n rules, the left n rules or the right n rules. Okay? The error bound in theorem 1 approaches 0 as n goes out to infinity. As we've seen with our applet, the more rectangles we include, the smaller that error gets, and therefore the error bound also gets smaller. And it follows that the left and right sums for certain functions approach the same limit as n goes to infinity. Theorem 2, limits of left and right sums. So if f of x is greater than 0 and is either increasing on AB or decreasing on AB, inclusive, then its left and right sums approach the same real number as n goes to infinity. Okay? So as n goes to infinity, it doesn't really matter whether you use the left n rule or the right n rule. Both of them will approach the same answer. So the number approached by the left and right sums as n goes to infinity is the area between the graphs of f and the x-axis from x equals to a to x equals to b. Example 1, approximating areas. Given the function f of x equals to 8 minus 0.1 x squared, find the approximate area under y equals f of x from x equals to 2 to x equals to 5. So we're asked to do 3 different things. For part A, graph the function over the interval from 0 to 6 inclusive, then draw left and right rectangles for the intervals using n equals to 6. So because we're asked to use n equals to 6, that means that we want six rectangles. And those 6 rectangles are going to go between 2 and 5 on the x-axis. Right? So even though we're graphing from 0 to 6, the area we're going to approximate ranges from 2 to 5. So it's a space of 3 units. Let's think about our delta x, for example. Our number line, let's say, starts from here. That's 0 to 6. So we're going to graph it from 0 to 6. But we're really only interested in the parts between 2 and 5. So here's 2, and here is 5. So that means that x sub naught is going to be equal to 2. And x sub n, where n equals to 6, is equal to 5. So x sub 6 is going to be equal to 5. And in between, the delta x is going to be equal to our formula, b minus a divided by n. So delta x is going to be equal to 5 minus 2, which is going to be 3, divided by 6, which will be 3 divided by 6, which will equal to 1/2. So delta x equals to 0.5, or 1/2. Okay, so that means that the next one right next to this is going to be equal to 2.5, and the one right after it will be 3, and the one right after it will be 3.5, and one after that will be 4, then 4.5, followed by 5. Okay, so let me write down the values. Here, so that means that x sub naught was equal to 2, x sub 1 is equal to 2.5, x sub 2 equals to 3, x sub 3, x sub 4, x sub 5, let's go a little bit higher here, and x sub 6, this would be 3.5, since the delta x is 0.5, so then 4, 4.5, and finally 5. So the space between 2 and 5 has been chopped up into little delta x's, right? Each one of these is a delta x, and delta x. They're all the same width, even though my drawing sucks here. They're all the same width of delta x, which is equal to 0.5. Now we're going to create rectangles, and the heights of those rectangles will depend upon the rule we use. So we're going to use the left. We're going to draw rectangles using the left rule, and we're going to draw rectangles using the right rule. And so we're going to evaluate the function, this one, at all the left end points to create the left rectangles, and all the right end ones to create the right ones. Now this is a parabola that opens down. This affects how wide it is, and then it's been shifted up by 8 units. So this is what it looks like. So let's just use technology to depict it. Okay, so here's all the rectangles using the left end rule. So with each rectangle, we go to the farthest left point. So in this case, it's this one. Let's put it in red. In this first rectangle, the farthest left point is a 2, so that's the one we use to establish the height. Right? That height right there is, coming back over here, that height is f of 2. That's how we get that one. The next rectangle, this purple one, the second purple one here, the leftmost point is that one. We've established from a second ago that all of these widths are a delta x, which is equal to 0.5. So that's how we know that that point right there is the point 2.5. And that is what we use to establish this height right there. Put it in red. We use to establish that height right there. And so that traces back down here to some value f of 2.5. Okay, so we keep going in that same manner all the way through, always using the leftmost point within the base of each rectangle to establish the height. And that's how we can get our 6 rectangles on the interval from 2 to 5 that will help us establish our estimate using the left end rule. Now using the right end rule, we're going to do the same thing with the domain. We got to go from 2 to 5. And we established already that each one of the bases is a delta x, which in this case is equal to 0.5. So we know that this little guy right here is going to be a 0.5. It's a delta x, all of them. That means that this point right there is a 2.5. And this is a delta x as well, delta x. That's why it makes sense that this point is a 3. Okay, so if we use the right base rules, within the base of each rectangle, we use the point farthest to the right. That's how we establish this height. So for this first rectangle, the height is going to be established by evaluating f of 2.5. Good. For the second rectangle, the rightmost point in its base is a 3. So we're going to use that to establish its height. And it looks like it's maybe somewhere around there. That's f of 3. equals to that one. Good. Okay, so then that's how we find all these rectangles, and that's what helps us establish our estimate using the right-hand rule. Okay, so now we can actually calculate it. Using the left-hand rule, we wanted to create these rectangles. So if we multiply the base, which we established to be 0.5, times the height of that first rectangle, which was f of 2, that product will give us the area of the first rectangle. This product will give me the area of the second, the third, the fourth, the fifth, all the way down. So f of 2, this value right here, to get an actual number, we follow our function, which is described right up here. So this f of 2 is going to be equal to 8 minus 0.2 times 2 squared. And then we multiply that by 0.5. So this product right here, all of this, will give me the area of the first rectangle. Plus, and now we do the same thing with 2.5. Okay, so in this calculation, f of 2 times delta x ends up being this calculation right here. So that would be that first one. And then the next one would be this one. The second rectangle is got a base of delta x times a height of f of 2.5, which ends up being this calculation right here. And the next one after that ends up being this one. And this one gives you that one. And so on and so forth. So this one is this one, and this one is that one. And finally, this one is the result of that one. So there you go. 1, 2, 3, 4, 5, 6 different rectangles. I can calculate, well, all of them have a base of delta x, which is 0.5. And I can calculate the heights by evaluating all of them at our function. And then if I crunch all that out, we get 17.23. Okay, so that's our estimate using the left rule and 6 rectangles for the area underneath the curve. Now using the right rule, R5, we can do the same thing. Okay, so using the right-hand rule, we see that the area of the first rectangle is this one. So let's put in this one right here is the first rectangle, which calculates to this one. With the base as 0.5, the height is calculated by evaluating our function at 2.5. The next rectangle is this one. Second rectangle is that one. And so on and so forth for the rest of them. Okay, so eventually we get an R sub 6, an estimate using 6 rectangles and the right-hand rule of 15.13. So the error bound for L6 and R6 is that the error is less than the absolute value, and then we use our formula. So it was f of b minus f of a times the delta x, which is equal to this. And so we see that the error bound is 2.1. The real error is definitely less than or equal to this one. Okay, part C. How large should n be in order for the approximations of the area by L sub n and R sub n to be within 0.05 of the true value? Okay, so using our formula for error, see that error is less than or equal to the absolute value of f of b minus f of a times delta x. And what we would want is for this to be equal to or less than or equal to this value. So let's set it equal to 0.05. Or we want to find n. Here, let me restate that. Find n such that this number is within that. So it's less than that. Such that f of b minus f of a in absolute values, delta x, is less than 0.05. Okay, so now where's the n? Well, the n is buried in here, right? So the formula for delta x is b minus a over n. Right? And then this is f of b minus f of a. Let's be less than 0.05. Okay, so the a and the b are 2 and 5. So this is absolute value of f of 5 minus f of 2, absolute values. And then this is the 5 minus 2 over n, less than 0.05. Okay, so now this can be calculated. We know our function value right there. So let's put that off on the side here. So note that, I'll put it over here. F of 5 is equal to 8 minus 0.25 squared. And f of 2 is equal to 8 minus 0.2 times 2 squared. So we can just use our calculator to figure out what this is. And once we have our values of f of 5 and f of 2, we can come back to our inequality and solve for n by evaluating f of 5 as 3, f of 2 as 7.2, and solving the inequality for n. Okay, so we get that n must be strictly greater than 252 in order for our error to be less than 0.05. Okay, so let's begin to define what we mean by the definite integral as a limit of sums. So the left and right sums are special cases of a more general sum called the Riemann sum that are used to approximate areas. So in general, let's say some function f of x is given. Let's for now assume that the function is positive, so it's above the x-axis, and that we're interested in finding the area that's trapped below the f of x function above the x-axis, and then sandwiched in between the vertical line x equals to a and x equals to b. So this region drawn over here in blue is what we're interested in. So the general process we're going to do is to come up with an equation that gives us the sum of the first n rectangles using either the left rule or the right rule. So we're going to begin by taking our interval from a to b. This interval here from a to b, we're going to take that interval right there, and we're going to find a partition. We're going to break it up into n subintervals so that each one of those subintervals becomes the base of a rectangle that we're going to draw. In order to properly break up that space, we need to think about how thick the base of each rectangle is going to be. So this is the formula we're going to use. Delta x equals to b minus a divided by n. That will always give you the width of each rectangle. It breaks up our domain into n subintervals of width delta x that partition off that little subsection from the segment from A to B. Okay, so as I break up this domain, the first one will be x sub 1, and then x sub 2, and dot, 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 dot. I keep going in that process until you get to the very last one. The very last one is going to be defined to be x sub n, and that's going to be equal to b. Okay, so following that pattern, we can say that the very first one is going to be x sub 0, since that one is 1. Keep in mind that the width of all of these is going to be delta x. So this is going to have a little width of delta x, the base of that first rectangle. The second one is going to be delta x, and so on and so forth, so on and so forth. Right before the end there is an x sub, and well, if the last one is n, the one that came right before it would be n minus 1. And the width there is still going to be a little delta x. Now, to establish a general pattern, let's think about what happens somewhere in the middle. Somewhere in the middle, we're going to get to this x sub kth value, right? X sub 1, x sub 2, x sub 3, dot, 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 all the way out to x sub k. So the one that came right before it, and I'm going to make it big so we can see it, but remember, they're all the same widths of delta x. The one that came right before it would be x sub k minus 1, and the width of it is still delta x. Good. Okay, so now if we're using the left-hand rule, that first rectangle that goes right over here, it's going to have a height established by the leftmost point, which is going to be f of x sub naught. So let's insert a rectangle there. So if we put a rectangle right here and we come up and we use the left-hand rule, it'll go up to there, approximately there. Where this is the point I used to establish the height, and that point is f of x sub naught. So looking at this sum here, that first multiplication of a delta x times f of x sub naught tells you the area of that first approximating rectangle. Good. Next, the one that came right after it, let's insert another rectangle there. So this time we put another rectangle there, and it goes up to, say around there. I know they're supposed to be the same width, but it's kind of ugly, but you get the point. So the second rectangle is going to have a height that goes up to there, and that is determined by this value, which is x sub 1. So this tells you the multiplication of these two tells you the area of that second approximating rectangle, this one. And that's how you get that one. And you keep going, and then you think about that very last rectangle. If you're using this left-hand rule, then the very last rectangle is going to be over here somewhere. It's going to look something like this. It's going to look something like this. And that point will tell me the height of the very last one, which is this one. Dot, 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 dot. It gives you this. Okay, somewhere in the middle, we can think about the kth one, the kth rectangle. And so just sort of in general, if we think about the kth one, it's going to have an f of, and then if we think about the kth one, the left end tells me the rectangle. Let's insert that one in there. So if there's a rectangle here going up to there, then this point right in there to the left tells me the height of that rectangle. And so somewhere in the middle here, we'll have the k sub x sub k minus 1 is what tells me the height of that middle rectangle. And they all have a width of delta x. So we can kind of stick that in the middle of that formula, dot, 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 all the way out to the last one. And so we can use this Riemann notation to express this exact same thing. Good, that's the left-hand rule. Similarly, we can find the right-hand rules, except for the right-hand ones, then we use the right point. So the very first rectangle will start off with a height established by using f of x sub 1 for the first rectangle, and so on and so forth. And so you end up with a rule that establishes the sum of the first n rectangles using the left-hand rule, and the sum of the first n rectangles using the right-hand rule. Okay, so this formula describes the sum of the first n rectangles using the left-hand rule. This formula describes the sum of the first n rectangles using the right-hand rule. And wait, there's more. There's something called the Riemann sum. This Riemann sum is very similarly connected to this, except that the height of each rectangle is no longer going to be tied to the left or the right-hand rule. It's going to be kind of a random selection. It could be anything, right? So that's what this picture over here is attempting to describe. So if you notice that for each rectangle now, if we think about the base of the first rectangle, we don't necessarily use the left endpoint or the right endpoint. We can just find some new value, C, right? That's what this C sub 1 is. Some new value C sub 1 that's somewhere in that base, C sub 1. Now, in actual practicality, we might not actually calculate it and know it, like get an actual number. We just know it exists. It's somewhere in there. Or we might choose a very convenient number that's somewhere in there. It could be the one right in the middle, or it could be one of the endpoints. Using the endpoints is allowed. It's just that we're opening it up even more and allowing the freedom to let C be some value, any value within that base of that first rectangle. Next, we look at the second rectangle, and we take a look at the base of the second rectangle, and we let C sub 2 be any value within there, right? And we keep going. So then for the third rectangle, this would be C sub 3, right? So C sub 1 is a value within this domain. So if we write it down, this is going to be brackets x sub naught to x sub 1, and C sub 1 is somewhere in there. And likewise, on the next set, from x sub 1 to x sub 2, C sub 2 will be somewhere in that set. And so on and so forth, and so on and so forth, until we get to the very end. And so we know at the very end, the value of B is equal to x sub n, and the one that came right before it would then be the value x sub n minus 1. So the very last set is going to be the set from x sub n minus 1 out to x sub n. And likewise, some value chosen within that base of that rectangle will be the value of C sub n. So there will be some value C sub n that is in that set. Let's highlight it again. So that would be that one. It'll still have the same base. So it'll still be a delta x width for that rectangle. They all have the same base. It's just that we'll use the value of C sub n to establish the height. So this is saying that the height of this rectangle is established by that point, which is determined by evaluating our function at the point C sub n. So the height of this rectangle would be f of C sub n. Okay, so instead of using the left rule or the right rule, we're going to use these C values, which are called sample points. And so if we come back over here and take a look at this formula, then this first product of f of C sub 1 times delta x corresponds to the area of this first rectangle. And the second one here corresponds to the area of this second rectangle, and so on and so forth, and we keep going in that pattern until we get to the very last one, and the very last one corresponds to this formula. So f of C sub n times delta x represents the area of the last rectangle. Okay, so to write down the pattern, let's think about one that's sort of randomly in the middle. As we keep going through this process, eventually we'll indicate that there's some value somewhere in the middle. We'll call that the x sub ith value. And the one that came right before it then would be the x sub I minus 1 value. So this is just a random rectangle somewhere in the middle of this process. It still has the same width of delta x. And then there's going to be some value chosen somewhere in there. That's going to be the ith value. Well, let's call it k. Some k value there. Oh, we used k up here. Let's just stick to k. So let's erase that. X sub k minus 1. And then this would be the c sub kth value. Okay, and so the interval here would go from x sub k minus 1 to x sub k, and c sub k would be somewhere in that interval. Okay, so using this this value in the center, that means that its height of this rectangle would be f of c sub k, and so this middle rectangle would have the area that's the product of a delta x times f of c sub k. And so now we can represent this sum of n rectangles as this, using this notation. It's the Riemann sum as k ranges from 1 to n of f of c sub k times delta x. If f of x is strictly greater than 0 on the interval from a to b, each term of s sub n is positive. So in the figure, f of x is strictly greater than 0, and f of c sub k is positive, so each term in the Riemann sum is also positive and corresponds to the area of rectangles with height f of c sub k. Right, so as we can see in this picture, the f of x function is strictly greater than 0, means it's positive. It's above the x-axis. So that would be this curve here. And as we can see, all the rectangles below it trapped between the function and the x-axis, as described by our s sub n sum, the sum of the first n rectangles, is going to be positive values. So corresponds to this idea of area. On the other hand, if f of x has both positive and negative values on the interval, positive terms of the Riemann sum s sub n represent areas of rectangles, and the negative terms of s sub n represent negatives of the areas of rectangles. Right? So our equation, the way we defined the areas of rectangles, would result in having positive answers when the function is above the x-axis. So our formula would be some positive height times a delta x, so we'd get a positive area there, a positive area there. But then for the cases where it's below the x-axis, for this case and for this case, we would end up getting a negative answer. So then when we add them, then the result of the Riemann sum would be the net result. It would be the positive areas minus the negative areas. All right, let's consider this example. Consider the function f of x equals to 12 minus x squared on the set from 2 to 4. Partition the interval into 4 subintervals of equal length. For each subinterval, let c sub k be the midpoint. Calculate the corresponding Riemann sum s sub 4. Okay, so we need to figure out our domain. So we're going to have some sort of an x-axis, and then we're going from 2 to 4 like this, and then we're going to break this up so that we can come up with 4 rectangles. The way we do that is we need to figure out our delta. Our delta x is going to be equal to 4 minus 2 divided by 4. Right? The formula is delta x equals to b minus a divided by n. So this is going to be 2 divided by 4, which is equal to 1/2, which equals to 0.5. So starting at 2, I'm going to add 0.5 to get to 2.5. 2.5. Then 3. I'm gotta make it bigger than that. It's got to be around 3 there, so that's about 2.5 there, 3 there, and about 3.5 there. Okay, so then this would be our x sub naught equals to 2, x sub 1 would then be equal to 2.5, x sub 2 equals to 3, x sub 3 equals to 3.5, x sub 4 equals to 4. Okay, so we have our sections. Now we need to think about our C sub k values. And so we're told to use the midpoints. The midpoint is going to be right in the middle. The way to find the midpoint between these 2 points is to add them together and divide by 2. So 2 plus 2.5 divided by 2 would be 4.5 divided by 2. 4.5 divided by 2, which is going to be equal to 2.25. And so that would be the value we're going to use for C sub 1. C sub 1 is going to be 2.25. We do the same thing, the same little formula for the next one. C sub 2 is going to be equal to 2.5 plus 3 divided by 2 gets you to 5.5 divided by 2, which is going to be 2.75. And that's the value of C sub 2, 2.75. Okay, we do the same thing for the others and we start to see a pattern. The next one is going to be C sub 3. No, put it up here actually. C sub 3 equals to 3.25. And finally, C sub 4 is going to be 3.75. Okay, so we have our C values, and now we can set up our sum to figure out the areas of 4 rectangles. Now all of them are going to have, all the rectangles are going to have a base of 0.5. So let me just kind of draw in some rectangles just to have something to picture. So just to visualize something, there's a rectangle there. Okay, so just so we can kind of visualize something, I just put in the 4 rectangles. And so they all have the same width of a delta x, which we know was equal to 0.5. So they all have that same delta x width, and delta x width over there. But the heights are unknown at this point, right? We haven't calculated them yet. So I'm not really sure how tall they're supposed to be, right? So this direction might change up and down depending on the value. And how we're going to figure that out is to figure out that this height has to be determined by the C sub 1 value. The height is going to be f of C sub 1, which in this case is f of 2.25, right? And that's how we'll figure out the area of that first rectangle, and then we do the same thing for all the others. Okay, so let's write down the summation. So S sub 4 is going to be equal to f of 2.25 times, well, actually, I'll just write down let's start by writing down f of C sub 1 times delta x plus f of C sub 2 times delta x plus f of C sub 3 times delta x plus f of C sub 4 times delta x. This has to be the area of all 4. So S sub 4 would be f of 2.25 times 0.5 or times a half plus f of 2.75 times a half plus f of 3.25 times a half plus f of 3.75 times a half. Okay, and now to figure out what each one of these is, we need to focus back on the equation that's given. So let me zoom out. So we were told that f is defined to be this guy. So that's what we use to figure out the height of each rectangle. We evaluate the function at 2.25, so that goes right in there. So f of x equals to 12 minus x squared. 12 minus x squared. So let me zoom back into here. So 12 minus x squared is the result of evaluating our function at this point. So this will be the height of the first rectangle times a half, where 1/2 is the base. Plus, now we've got to do the same thing with the next function. This will be 12 minus 2.75 squared times a half plus 12 minus. Okay, so now all we have to do is evaluate this sum. This would be a good time to use use your calculator, use the table function of your calculator. Okay, so let's go over to y equals and type this equation in. It's going to be 12 minus x to the power of 2. 12 minus x squared. There it is. Okay, so then we're going to go over to our table, delete anything else that's already in there, and type in our values. So the first one is 2.25. It'll automatically square it. And while we're at it, I suppose I might as well just multiply by a half as well, huh? So let's go back to our equation, and let's wrap up the whole thing with parentheses. Parentheses 12 minus x squared, close parentheses, times 0.5. That way we take care of the whole thing all at once. So let's go back to our table, second shift table, delete. Okay, so 2.25, oops, clear. 2.25 is the first one, followed by 2.75, followed by 3.25, and finally 3.75. And we get a negative. Okay, so here is a case where the rectangle will actually go below the x-axis, not above. Okay, so we just have to add up all these numbers. I'm going to copy them onto here and then add them up, and that'll be our answer. Okay, and once we add all those values up, we get S sub 4 is equal to 5.3754. They said to round to 2 decimal places, so S sub 4 is 5.38. And that would be my final result. So we can achieve the same thing using this online graphing applet found here at this address. Now let's type in the equation. It was 12 minus x to the power of 2. So let's zoom out. There it is. So there's the graph 12 minus x squared. It's a parabola upside down and then raised up to 12. Okay, and we were interested in the region between 2 and 4, and we were asked to make 4 rectangles to approximate that area. So the real area we're interested in is this graded region, right? So part of it will be above the x-axis, and part of it will be below the x-axis. And we're going to approximate using these 4 rectangles. So they would look like that. Okay, so 4 approximating rectangles. We know the base of each one of these was 1/2. And each one of them, the height is determined by evaluating our function at the various c sub 1 points. So this ranged from 2 to 4, so there's a 4 there, from 2 to 4. The center of this first rectangle that we used to establish the height, that's a c sub 1, that's the c sub 1 value from over there, 2.25. And then this would be the next value of 2.5. And then the center of this second rectangle that's the C sub 2 value of 2.25, and then C sub 3 is the center of that rectangle, and finally C sub 4 is the center of that rectangle. So we found out that this area here has the value of negative 1.031. That would be this one. And this one here, it has the value of 0.7188. This one here, from here to here, this one is the 2.2188. And finally, this first one, that one is the area of 3.4688. 4688. Okay, so if we add up all four blue rectangles, they add up to 5.38, which is our best estimate, the sum of the gray region above the x-axis minus the gray region below the x-axis. Back on our applet, we see that the midpoint rule here tells us that same result. And also we have the benefit of knowing the real answer right here, 5.33, so we can see that this is actually a pretty good estimate of that. Theorem 3, the limit of Riemann sum. So if f is a continuous function on a to b, then the Riemann sums for f on a to b approach a real number limit I as n goes to infinity. Okay, so as we can confirm with our applet, sticking to that same equation we were just using, as we increase n, as n goes to infinity, that means that n controls how many rectangles we have. So if we increase n, we increase the number of rectangles. And as the number of rectangles increases, we see that the summation of the rectangles, so the positive rectangles above the x-axis minus the rectangles below the x-axis, we figure out whatever that sum is, and that sum will get infinitely close to the real answer, which again we can see from this applet. We have the benefit of finding that answer here. Okay, so as n goes to infinity, our approximation gets better and better and better, and it approaches a constant. And finally, we arrive at the formal definition of a definite integral. So let f be a continuous function on the set a to b. The limit capital I of a Riemann sum for f on a to b, guaranteed to exist by the previous theorem, is called the definite integral of f from a to b and is denoted using this notation, right? It's like an elongated s, right, representing sum, because it's a sum of rectangles. But it's an elongated s called the integral. And then these, the a and the b, are called the limits of integration. The value of f of x, whatever function's in here, this value is called the integrand. And then the lower limit of integration is the a, and then the upper limit of integration is the b. So remember that when we talk about area is always a positive thing. So it's a positive value. The definite integral has the following geometric interpretation. So if we're looking at the integral from a to b of f of x dx, that represents the cumulative sum of signed areas between the graph of f and the x-axis from a to b, where the areas above the x-axis are counted positively and the areas below the x-axis are counted negatively. Okay, so it's a slightly different thing. If I just found you to asked to find the areas of A and B, area A is positive, area B is positive, we would just add them together and that would be the area. Whereas here, we want to count the area above the x-axis to be positive, and whatever area is below the x-axis is thought of as a negative number. And so if I wanted to find the integral of this function from a to b, integral from a to b of f of x dx, we would have to find the area A and then take its negative because it's below the x-axis. So it's negative A plus B. So the answer might be a negative, right? From the picture, it looks like this area in gray might be a little bit bigger than the one in blue, or it might be 0 if they are equal to each other. Maybe they kind of cancel out and we get the answer to the integral is 0. Let's look at an example. Okay, so let's say that this graph is given and these areas are provided for us. So areas are positive. So area B is 11.9 units. Area C is 7.67 units. And area A is 2.12 units. Okay, so now if we are given that and we're asked to find the integral from a to b of f of x dx, we can see that it's somehow connected to these values, but it's a little bit different. So I'll put it in blue here. So because I know that the area is below the x-axis, from a to b, f of x, it's gonna be this area right in here. The integral from a to b on f of x, and I can see that this is going to be equal to negative 2.12. Right? I just had to introduce the minus because I know it's below the x-axis. I'm just using this area. Now if we're asked to find the integral from a to c, that would be from here, a, all the way out to c, that would be both the area of b, which is positive, and then plus area b times a negative because it's below the x-axis. So this is equivalent to negative area A plus B, which would be negative 2.12 plus 11.9. And so the integral, here actually let me just say, okay, so then the integral from A to C on f of x dx is equal to 11.9 minus 2.12, 9.78. 9.78. Okay, so now the integral from a to d on f of x dx, well, that's going to involve the entire image. So here's a all the way out to d. So this is going to be equal to minus a plus b plus negative c, or minus c. This will then be negative 2.12 plus positive 11.9 plus negative 7.67. Good, so this one's a negative, this one's a negative. Okay, and so we just figure out what that is. We get 2.11. 2.11. So the integral from a to d of f of x dx equals to 2.11. Good, so it's the area above the x-axis, that's the b, minus the area of a minus the area of c. Okay, so here are some properties of definite integrals. The integral from a to a of f of x dx equals 0. The integral from a to b of f of x dx equals to negative 1 times the integral from b to a of f of x dx. So for number 2, notice that what we've done is that we've flipped the limits of integration. If we go from a to b, we can reverse that process and go from b to a if we want to, and we just have to introduce an extra minus out in front. The third one says that if we have a constant k here times our function f of x, then we can factor out the k, remove it from the integral, calculate this new integral, and then later multiply it by k, and we get the same result. The fourth one says that if we have a plus or a minus in the integrand, then we can separate it this way. So the integral of a sum of functions is equal to the sum of two different integrals. Likewise with the subtraction. So we can add or subtract, have an addition or a subtraction of two different functions, and then restate that as the addition or subtraction of two different integrals, right? Just like this. And finally, we have that the integral from a to c of f of x dx is equal to the integral from a to b of f of x dx plus the integral from b to c of f of x dx. Okay, so instead of going from a to c, we can separate it into two separate integrals where we still start off in the same place, a, we go to some value b, and then we start a new integral at that value b and go all the way up to c. So the sum of these two integrals will be equal to that one. Okay, I know I didn't prove any of these things. We're just accepting them to be true. We just got to learn what they're saying and then apply them. Use them, apply them, and let's do some examples that take advantage of these properties. Okay, so let's say that this information up here is given to us. All three of these integrals are given to us. That the integral from 1 to 3 of 2x dx equals to 8. That the integral from 1 to 3 of x cubed dx equals 20. And that the integral from 3 to 4 of x cubed dx equals to 175 divided by 4. So these three are given. So we're asked to use these three integrals plus the properties of integrals that we were just provided to simplify or solve to identify these other integrals. Okay, so for example, for part A, the integral from 1 to 3 of 4x cubed. So notice that that looks an awful lot like this one. Like this one, from 1 to 3 of x cubed dx. And we know that's 20. Luckily, one of our properties says that the 4, which is a constant, can be brought out. So for this one, I would say that the integral from 1, so for part A, I'd say that the integral from 1 to 3 of 4x cubed dx, thanks to one of our properties, is equal to 4 times the integral from 1 to 3 of x cubed dx, right? So we can pull out a constant. And now I see that this integral is this one, which is just equal to 20. So this integral right here is this one. Exactly, the same limits and everything. So it's equal to 20. So that means that the whole thing equals 80. Okay, for this next one, we are going to use some properties to separate this. We know that when we have a difference, a subtraction in our integrand, we can rewrite this as the subtraction of two different integrals. So the integral from 1 to 3 of x cubed minus 2x dx is going to be equal to the integral from 1 to 3. We keep the same limits of x cubed dx minus the integral from 2 to 2x dx from 1 to 3. So we keep the same limits of integration. We just get to separate it into the difference of two integrals. And next, we know that we can pull out a 2, because that's also a constant. So this will become the integral from 1 to 3 of x cubed dx minus 2 times the integral from 1 to 3 on x dx. And now, this first part is equal to 20. Right? This is 20. It's this integral from 1 to 3 of x cubed dx. And, oh, actually, I shouldn't have pulled out that 2, since this is the integral of 2x dx equals to 8. So, should have been paying more attention. This is just going to be the 2x. Let's leave it alone. And now that whole thing is equal to this guy. Pay attention to the limits as well. It's got to be the same limits and everything. So this whole thing is really just going to be an 8. So that means that our answer is just going to be 20 minus 8, or 12. So this is going to be 20 minus 8 equals to 12. So I'll just write down the whole integral down here. So therefore, the integral from 1 to 3 on x cubed minus 2x dx equals to 12. Probably should have done the same thing over here. The integral from 1 to 3 on 4x cubed dx equals 80. Box that up. Okay, for the third one, these two are very, very similar, except this went from 1 to 3, whereas this goes from 3 to 1. So one of our properties says that we can flip-flop these. We can interchange the limits of integration if we introduce an extra factor of -1. So the integral from 3 to 1 on x cubed minus 2x dx is equal to -1 times the integral from 1 to 3 of x cubed minus 2x dx. And now this one looks just like part B, so I can just insert it there and say that this is going to be -1 times 12, where I'm saying it's 12 by referencing this down here. Or I can just copy all that work again, but that's where I'm getting this 12 from there. So I'll say that the integral from 3 to 1 on x cubed minus 2x dx is equal to -12. Box that up. Next, for part D, the integral from 1 to 4 on 4x cubed dx. From 1 to 4, this goes from 1 to 3, this goes from 1 to 3, this goes from 3 to 4. So there isn't any integral that goes from 1 to 4. So we're going to have to use one of our properties, the last property, I think is the fifth property, to introduce the value 3 so that I can rewrite this as the sum of two integrals. So I'll say that the integral from 1 to 4 on 4x cubed dx is going to be equal to the integral from 1 to 3 on 4x cubed dx plus the integral from 3 to 4 on 4x cubed dx. That's a really ugly integral sign. Let's rewrite that. The integral there. And the reason I did that is because now this is an integral we know. There it is. And this is an integral we know as well. So just based on the integrals that were given, that means that this guy is going to be really close to that one. I just have to move that 4 out of the way. So this is going to be equal to 4 times the integral from 1 to 3 on x cubed dx plus 4 times the integral from 3 to 4 on x cubed dx. And so now this is equal to 4 times 20. Right? All of this is exactly equal to that. 1 to 3, x to the third power dx equals 20. So that'll be this 20. Plus 4 times, and now this one, and that's a really ugly thing, this one, which goes from 3 to 4, this one is exactly that one. Integral from 3 to 4 on x cubed dx, integral from 3 to 4 on x cubed dx. This one is going to be exactly equal to this fraction of 175 divided by 4. 175 divided by 4. Okay, so luckily these two will reduce, they will cancel, and those multiply to 80. So I get 80 plus 175, which is equal to 255. So I can restate the whole thing then. The integral from 1 to 4 on 4x cubed dx is equal to 255. Okay, finally, we got to answer part E, and I'm running out of space here, so I'm just going to move that question over here. And let me zoom into here. Okay, the integral from 11 to 11 on x to the third power dx. And this one's a really easy one because one of our properties indicates that when we're integrating from a, right, the integral from a to a on f of x dx just equals to 0. We're integrating from the same value to the same value. So if the lower limit and the upper limit of integration are the same value as they are here, then this is an easy one. The answer is just 0. Anytime this number is identical to that number, then the answer is going to be 0. Okay, so there's the answer for that one, and we're done. Okay, so this was a really nice problem that forced us to use the properties of integrals. And hopefully we've covered enough material to help you do your homework. So please work on your homework and come by my office hours if you have any questions.